later.
Is the recording really necessary? Because textbooks are available. Because normally in a class, I'm doing it like a class. So what I would recommend, you come the way you attend a class, come with notebook and pen. Okay, because we are following the timetable schedule. So it is like a normal class. So then the so if we consider a system, I'm following the FM White convention that the system encloses a fixed mass and the control volume is a specified region in space. That region could be moving with time, moving with constant velocity, or moving with variable velocity. For simplicity, we'll consider control volume to be fixed in space. When I say fixed, I mean fixed with respect to the laboratory frame of reference, which we assume is a inertial frame. So Newton's laws apply in that frame. So now we know that if I consider a fixed mass of material, then I can apply the conservation of mass and the conservation of energy. At the moment, I'm talking of conservation of mass and conservation of energy, because in this 1/3 of the semester, we'll be covering thermodynamics. So later, when we come to fluid mechanics, then we'll talk of conservation of linear momentum, conservation of angular momentum. So I know how to apply conservation of mass, conservation of energy to a system. If I consider a control volume, it's not very clear how to apply it, because apart from energy Q being supplied and energy W being expended by the system, I also have energy being carried along with the mass which is crossing the boundary of the control volume. The boundary of the control volume, there's a shorter name for it, control surface. So if material is crossing the control surface, that may be carrying certain amount of mass, that may be carrying certain amount of energy. So if I consider a control volume, what is the final energy in the control volume compared to what is the initial energy? It is not just Q and W, it is the flow across the boundary which also plays a role. So then the reasoning is, I don't have to bother about all those flows if I consider the system. So now if I can relate the rate of change of a property for a system to the rate of change for the control volume, then I know how to apply it to a system. If I know how the system is related to the control volume, then I can get the law for the control volume. So we know how to apply it to a system. We must now learn how to relate the rate of change of a property for a system to the rate of change for a control volume. So that is where I was starting in the last class. I said, let's say I have a control volume. Now, if I have taken this from Streeter's book on fluid mechanics, Streeter denotes the control volume by a solid line and the system by a dotted line. I'm reversing the convention, reversing it with a reason, because there's mass flow across the boundary of the control volume. So showing that as a dotted boundary seems more logical. So let's say this is my boundary of the control volume. And at time t, I choose my system to have a boundary which coincides with the boundary of the control volume. Now I let an interval of time elapse, an interval which is delta t. So in that time delta t, the control volume, I said for simplicity, we'll take the control volume to be fixed in space. So that remains where it was. Now let us say the material in the control volume has a velocity in this direction. In that case, if I follow the material moves with the velocity at every point. So then the system boundary will move with the velocity of the material. So the system has moved to this location. So then at time t plus delta t, if I see the system, in some places it has moved out, in some places it has moved in. So I denote the regions as 1, 2, and 3. Region 1 is the region which is part of the control volume, but at time t plus delta t is no longer part of the system. Region 2 belongs to the system and control volume at t plus delta t. And region 3 is the region which is now part of the system, but it is not part of the control volume. So then what we are trying to do is let us say B is equal to some intensive, beta is the intensive property, and it is equal to the value of B per unit mass. So then my question is, this is what we need to figure out. So let's start from the very definition. dB system would be the value of B for the system at t plus delta t minus a value of B for the system at t divided by delta t, limit delta t going to 0. So now the extensive property would be the value of B over each region of space. So let me consider the regions separately. So at t plus delta t, the system contains region 2 and region 3. So this is B system at t plus delta t. From this I have to deduct B system at t. So at t, the system included regions 1 and 2. So I'm integrating in order to get B for a certain region. I multiply beta, which is B per unit mass, into the mass of an element. The mass of an element is density into the volume element. So that I integrate over the region and evaluate at appropriate time. Now this I must relate to the control volume. Now the control volume, if you see, regardless of time, it is regions 1 and 2. So in order to get the derivative of B for the control volume, I add region 1 and I drop region 3. So then this will be the value of B for the control volume at t plus delta t minus but then in order to get this expression, I must now subtract for region 1 and add for region 3. So I brought the 3 over here and I've added a region 1 over here and subtracted it here. So this expression is same as this. Any questions?
Sir,
Yeah.
sir, control volume is always remain fixed.
I'm assuming for simplicity. Control volume.
Yes, sir.
Control volumes in principle could be moving with specified velocity, but since we are trying to cover thermodynamics as well as fluid mechanics in one course, I'm trying to keep it simple. Okay, so for that reason, instead of putting in all generality right in the beginning, because right now you have just finished your common courses and you're starting with your engineering courses. So let's not introduce unnecessary complication, because quite often the control volumes which we'll be using will be fixed in space. So I'm assuming that it is fixed in space. When I'm saying fixed in space, I mean fixed with respect to the laboratory frame of reference.
Okay, sir. Sir, and means volume is means volume is also fixed, right?
It's a fixed region in space, so
Okay,
that
sir.
volume is fixed.
Okay, sir.
So now we have got this relation between the rate of change for a system to the rate of change for a control volume. The two are connected by this equation where you have these two additional terms. The two additional terms involve region 1 and region 3. So if you see, region 1 and region 3 are the regions which are related to the inflow and the outflow. So then what is that region can be relate to the rate of flow. So the rate of flow would be determined by the velocity, because the system boundary is moving with the material, so it is moving with the velocity of the material. So let us now expand that slightly. And let us say these are the velocities at these two locations. So this is an idiosyncrasy. I don't know why it has happened, but velocity in the first course on fluid mechanics is always denoted with a capital V. And when you do the second course on fluid mechanics, then it becomes a small v. Why it happens, I don't know. But since this is the first course, I'll denote velocity by capital V. So capital V is the velocity with which material is moving at that location. So then, if I see the outflow region, then in time delta t, the boundary would have moved through a distance which is v into delta t. So then the rate of change in the system is related to the rate of change in the control volume through these terms, and these terms involve the integral of beta over this region, the region through which the boundary has moved. So then in order to estimate how much it is, I must know what is the volume. So then in order to calculate what is the volume, we must know what is the region through which the boundary of the system has moved. So the system boundary which follows the material will move with the velocity of the material. So the boundary will move through v delta t in time interval delta t. So if I consider an area dA, then the volume covered in region 3, the region through which the system has moved out from the control volume, would be the volume of the cylinder which has base area dA and slant height v delta t. Because why I say slant height, the area of the base area is a vector quantity. The vector quantity has direction normal to the area. That direction may not be same as direction of the velocity. So then it will not be a right cylinder, it will be an inclined cylinder. So then it has base area dA and slant height v delta t. So the dV would be into cos alpha, the cosine of the angle between dA and V. So that can be written as so then the area the area vector is always taken to be the outward vector. So in the outflow area, if if A and V are aligned, then I would get this volume. So then in region 3,
So can you please explain how did that dv come? I'm not getting it.
the velocity at this the region 3. So the region 3, the region 3 comes about because the system boundary has moved compared to what the boundary of the control volume is. Okay. So that moves, the system boundary moves with velocity v, because the system is following a certain mass of a certain amount of material, so it is moving with the material. So if the material has velocity v, the system boundary must be moving with velocity v. Yeah. Now my region 3 by definition is the region over which the system, which is now included in the system at t plus delta t, but it was not in the system at t. So how much is that region? That region is the region through which the system boundary has moved in time interval delta t. So that boundary at any point must move by a vector distance v delta t. Great. Now, if I consider a certain element dA of this outflow area, so if I consider what is the volume through which the material which flows out through dA, how much volume does it cover? That if I integrate over the entire outflow area, that will give me the entire volume of region 3. So then let me consider a small element dA. So that element dA has a certain direction. The velocity may not have the same direction. The direction of the area is the direction of the normal to the area. That is how the vector area is defined. So then the region through which dA moves out. So dA was an element of the area of the control surface. This element, so this element was also part of the boundary of the system, but for the system it moves out by a distance v delta t. So then it will cover a cylinder which has a base area dA and slant height v delta t.
Yes, sir. I got it.
So then if v delta t is the slant height and dA is the area and cos and alpha is the angle between the velocity direction and area, in that case my dV would be dA v delta t into cos alpha, because I must take not the slant height but the component perpendicular to the base. So if I have a cylinder with this slant height and this base, then I can divide it into segments and slide them so that it will come here. The volume is not changed, but then now I have a right cylinder and I know its volume is base into height. So the inclined cylinder also, which can be transformed to this by just cutting it into infinitesimally thin sections and moving it, has the same volume. So this inclined cylinder must have the same volume as this. So its volume, the volume of the inclined cylinder must be base area into the perpendicular height. So the component of the slant height in the direction normal to the base. So that is what I have taken here. So in the outflow area, the cos alpha is the angle between dA and V. So then dA dot V is dAV cos alpha. So this is what I've written.
Yes, sir, got it.
Okay. Now in region 1, okay, here cos alpha is negative, so the dV would be minus dA V delta T into cos alpha. So here this is what it is. So therefore, if I see the terms which express the difference between the derivative of B for the system and for the control volume, I had a minus this here and a plus this here. So what I had was so now we showed that for the inflow region there is a minus here. So then this delta t here, delta t here, this delta t cancels with this delta t. Now all of these were evaluated at t plus delta t. Now in the limit, let me first cancel this. Now if I evaluate this at t plus delta t, I could express that as a Taylor series, but then the value at t would be the leading order term, and then in the limit delta t going to 0, the remaining terms would go to 0. So then in this limit, now the inflow area and the outflow area, if I add both of them, it means that I'm including the entire area. So this would be so CS denotes control surface. Control surface is the boundary of the control volume. So this was at t plus delta t. So this to leading order, it is the value at t. Now since the equation in, so I was taking delta t only to get the expression for derivative. So finally when I write the relation, I can assume that everything is evaluated at delta t. Everything is evaluated at t. So then I had this expression. Now this I have related to integral over the control surface. So then,
Sir?
yeah.
Sir, why integration of means from inflow area
Yes.
plus outflow is control surface?
Because okay, there'll be some point at which the velocity is 0, but that will usually be a point. And if it is 0, their velocity is 0, so that doesn't contribute anything. So anywhere where there is inflow or outflow, if I include everything, then it gives me the total control surface. So to this I could have added a zero flow area. So on the surface, either there'll be an inflow or there'll be an outflow or there'll be zero flow. If there is zero flow, then V is 0. So and that portion will not give me anything. So then over the control surface, if I expand this, I'll have three terms: inflow area, outflow area, and zero flow area. On the zero flow area, V dot dA is 0. So that cancels out. So then I am left with inflow area and outflow area. Okay.
Okay.
So dB system by dt So this tells me how the rate of change of a property for a system is related to the rate of change of property for a control volume. So to the system I can apply it. So if B of system, so if capital B is the mass, then the mass of a system remains constant. So del B control volume, del M control volume by del T must be equal to the this integral over the control surface, where if my B is mass, then beta is the mass per unit mass, which is unity. So then over the control surface, rho V dot dA must be equal to 0. So that would be the conservation of mass applied to a control system. B is equal to mass. So then beta is equal to 1. We know sorry. Now, if I have a situation where the local value of all properties does not change with time. So let us say I have a nozzle where fluid is flowing in, flowing out. In that case, if I consider any point inside so let us say this is my control volume. So at any point, if I see if the nozzle is operating at steady state, I expect the density would not change with time. If the density doesn't change with time, if I integrate density over volume, that should remain unchanged. So then, if I have something called steady state steady flow, in that case, the property in a control volume does not change with time. In that case, I have, if I assume steady state, steady flow, so this is the statement of conservation of mass for a control volume. Now I'm following the way in which this was deduced in the book, but probably a simpler way would be let us say whatever machinery I'm dealing with, could be a boiler, could be a turbine, I could represent it schematically in this manner. If I represent it schematically in this manner, I could further assume that assumption is usually made, although we don't state it very explicitly. Let us say I have flow occurring through an inlet pipe and flow occurring through an exit pipe. Now, the fluid is a viscous fluid which is flowing through these pipes. So if it's a viscous fluid, now this is so at this point I'll state a result which you still may not have studied, probably not in school. The question is, if I have flow through a pipe, is the velocity uniform or does it vary across the cross section of the pipe? So this is the part which we'll do in the later part of the course, but let me just take the final result. If it is a laminar flow, we have something called laminar flow and turbulent flow. So when material flows through a pipe, if the flow velocity is small, it is what would be considered small? That is determined by a certain parameter called Reynolds number. So if the Reynolds number is small, so at the moment, let's say if the flow rate is small, in that case, it remains laminar. But if the flow rate is very high, it becomes turbulent. So if it is laminar flow, in that case, the velocity profile is parabolic. If it is turbulent, then it's a more fuller profile. So instead of being peaked, it is flatter. But regardless of that, you have a certain profile. So depending on the flow rate, you could have different profiles of the velocity across the pipe. But in most of our engineering calculations, when we are dealing with an entire machinery and we have an inlet pipe and an exit pipe, we normally take only one value of the velocity for the pipe, which is the average velocity. So we divide the flow rate by the cross-sectional area, and whatever velocity that gives us, we take that as the velocity. So then, if I assume that this is my equipment, then if I have uniform flow inside, uniform flow in the inlet pipe and exit pipe, then I can say my I can take my system to have a boundary at time t. I take this as my system, and at time t plus delta t, I deduct this part and add a VE delta T. So I take my system to have this boundary where this is VE delta T at time T plus delta T. And then from these two, I can again write down the relation between the derivative of a property for the system and for a control volume. So that derivation will turn out a little simpler than this. It will not have these V dot dA, etc. So I'll leave it as an exercise for you to reason it out from this simpler configuration. Anyway, our time today is
Sir? Sir?
Hello, sir, you are muted.
Sir, you are muted, I guess.
Sir, you are muted. We